is that in this class, it's really easy to get yourself in the weeds if you just start proving, right? Oh, I'm gonna do question 2, and you start writing. And then you get halfway down the page and you've written this morass of mathematics and you have no idea how you got there and you have no idea where you're going. You just have this brick of math, right? So go in with a strategy about what you're trying to do. It's okay to take a couple of 30 seconds or a minute to figure out, okay, first step, I'm going to do this. Second step, I'm going to do this. Third step, I'm going to do that. Just like 1 or 2 words about what you want to do. So you got an outline of what the approach should be, okay? Because if you don't have an outline, you can occasionally stumble across the answer to a problem just by proving your way through it, but it's difficult to do that. Okay? So be careful with that. Yeah, so have a plan on each question. It's not like a calculus class where you can just decide like, oh, this is the type of question, I'm just going to start doing it, it will do itself. A lot of times there'll be some move in the middle where you have to be really concrete about what it is that you're doing, really specific about the idea to be invoked. The third thing is, oh my gosh, please, even if you got to use flashcards to do it, know your definitions. I can't ask you complicated questions on the exam. I can only ask you 1 or 2 line questions, right? Like questions with 1 idea or 2 ideas inside of them. But the way they have to be asked in terms of the definitions. So if I write down, show something is in the null space, or show that something is a direct sum, or show that something is in the range, or show that something is an isomorphism, and you don't know what those words mean, if you don't know what it means to be in the null space of an operator, if I ask you a question about null spaces, you're dead on the water. You can't even get out the gate. You have to know the definitions. Okay? Like it's really not just for the definitional section, but all the rest of the exam is going to be written in terms of the definitions too. So make sure that you can do this, right? If I say, what's the null space of a vector of an operator, you can just write it down. And then I say, what does it mean for a vector to be in there? And you'd say, oh, well, that would mean that TV is equal to 0. Right? You should know that stuff. It should be immediate. And that's not stuff that's hard. That's just stuff that takes time. Okay, so practice those things. All right. Are there any other questions about that stuff before I move on and talk about upper triangular matrices here that I can answer? Okay.
So in the video, you said that you use the polynomial structure to create a new operator and an existing operator, and that's how you get your T.
Yep.
Where does the existing operator come from, and where does the operator you already have?
So, I mean, the T here is just usually given to you,
Yeah.
right? That's like, so T you just given a T, right? So here's T. T is in L of V, right? You just get that, somebody comes along and hands that to you. And the idea is, well, can you make new operators out of old ones, right? What do you get for free that you know is an operator if that is an operator? And the idea is, well, if T is an operator, then certainly T composed with T is an operator because T goes from V to V and T goes from V to V. This is a meaningful object. So that means I get T squared. So if T is an operator, T squared is an operator. And likewise, all of the Tn's are operators, right? Because this is a meaningful object. Okay, now L of V is a vector space. And to be a vector space means that linear combinations of vectors in the vector space remain in the vector space, right? If you're a vector space, it means that you're closed under linear combinations. So that means, well, if T is in here and T squared is in here and T cubed is in here, all the way up to TVN being in here, then I can take linear combinations of those guys. Well, this is just a, also I guess with the identity matrices in there too. What that means is that you can think of this as C0I plus C1T up to Cn TVN. This is also an operator because all of these are in V or in L of V. And L of V is a vector space, so I can combine them up this way. So that's what I meant by polynomials are used to get new operators from old ones.
And so how is that? And this is just something that you can do.
Yeah.
Like that's why we want to
Yep.
do it. Okay. So
Yep.
it's basically the point is like you can write a linear combination.
No, yeah, that you could write a linear combination, not just of operators, but of powers of operators, right? And then the big move here is that you think of this as being P of T, where P of Z is equal to C naught plus C1Z up to CMZV, right? There's this connection between the vector space of operators and these complex polynomials that you have. And the fact that you have this connection means that here you can use algebra, like polynomial algebra. So there was a point I made earlier today, which I want to emphasize because it came up in the homework. This is a very important point. So can anybody tell me what the zero property says? The zero property for complex numbers or real numbers, that's what? No. That's true, but that's not what it means. That's the fact that, yep. You're saying more than I want. If I, nope, that's the fundamental theorem of algebra. If that statement is true right there and A and B are numbers, what do I know about A and B? Either A is 0 or B is 0, right? A is 0 or B is 0. We use this all the time when we're factoring polynomials, right? The thing is, because products that equal 0, if you're a number, if you have a product of numbers that's equal to 0, either one of the numbers must be 0. That has to be true. Notice one of the most important things about when you start studying operators, and this matters for these upper triangular matrices too, this is relevant to what we're talking about, is the idea that that is not at all true for operators, right? So in fact, I think Axler asks you to do this. He asks you to find operators, neither one of which is 0, that combined are the 0 operator. So for example, this matrix and this matrix, that's not right one. Oh, I missed this completely. 1, 0, and 1 here. Yeah, that's 0, and that's 0, and that's 0. So this is the 0. The product of those matrices is 0. So the linear operators they represent, is that the 0 matrix? No. So what I've just shown you is just because you have operators that multiply up to the 0 operator does not mean you get to say A or B is the 0 operator. You can't do that. There is no 0 property for operators, none. So there is no 0 property for operators. Now I'm going to connect this up to the homework question, to a homework question involving polynomials. What you would love to do, what you would absolutely love to do, if you had an expression like this. If somebody came along and said, look, 2 minus ti times 2 minus 3i times t minus 4i is 0. What you would love to do is to say, oh, well, I'm going to use the 0 property because obviously if I have a product of things that's equal to 0, then one of them must be 0. So if somebody says, oh, prove that so here's a wrong proof. I'm gonna give you a wrong proof that 2, 3, or 4 is an eigenvalue of this thing. Okay. Well, either t minus 2i is equal to 0, or t minus 3i is equal to 0, or t minus 4i is equal to 0, which means either t minus 2iv is equal to 0, or t is minus 3iv 0, or t minus 4iv is 0, which means t is equal to tv equal to 2v, or tv is equal to 3v, or tv is equal to 4v. Now that looks right. It looks right. In fact, some of you have this written down in your homework like this. This looks like a correct argument. But to do this, you have invoked the 0 property. You factor something and then say, oh, well, since the product is 0, one of the pieces must be 0. But the problem is this is false. Can't factor polynomials and set them equal to 0, or sorry, factor operator expressions like this and say any of the pieces are equal to 0 because this can happen. Each individual piece could be non-zero, and yet in total, they could be, each individual piece could be non-zero in a product that multiplies up the 0 element. Okay? They could just miss each other entirely. So this is ultimately let me make sure I put Just so that in 1,000 years when the aliens find this on the archive of the internet, but they don't think I meant this. This is a false argument. Because there's no zero property. Okay. So when you're doing this argument, the reason that you have to use the polynomial stuff, or these like arguments where you involve the kernel, where you have to get the vector v involved, is the only reason that this is true, that these eigenvalue expressions are true, is because you're working with an eigenvector. Nowhere in here did we use where did we use the assumption that TV was equal to lambda v in here? This is a big red flag when you're doing an argument, right? One of the hypotheses of this question was that TV is equal to lambda v. Okay, so the most elegant solution to this problem is to first prove exercise 10, and then go back and use it to do exercise 2. So exercise 10, did I assign exercise 10? Okay, exercise 10 is beautiful because exercise 10 says that if TV is equal to lambda v, then PTV is equal to P lambda v. What would that mean? That would mean if this was true, then once I've applied this to a vector, I can't do anything unless I apply it to a vector, but I could say this, T minus 2i, T minus 3i, T minus 4iv is equal to 0. That should be true, right? All I've done is I just applied this operator to a vector, and it's also equal to 0, so I can apply it to an operator, a vector as well. And now what? Well, this fact, however you get here, what this fact says is, if TV is equal to lambda v, the polynomial in T, all of this is P of T, can be replaced with P of lambda. However you get here, either you do exercise 10 or you one approach to this question is to prove it sort of for this particular case. However you do it, what you're going to end up with is this. Lambda minus 2i, lambda minus 3i, lambda minus 4i v is equal to 0v. Why do we need all the i's in here? Because that doesn't make any sense all by itself, right? I mean, there's identities running around in here. It's an operator still, but all the i's hit the vector v, and you end up with this expression: lambda minus 2, lambda minus 3, lambda minus 4 v is equal to 0. Now what? What sort of object is this? Is that an operator or a number? It's a number. It's just a number. And guess what? Numbers satisfy the 0 property. So the correct version of this argument requires that you reduce an expression in operators to an expression in numbers. And this thing has terms that must equal 0. How do I know that, by the way? Something v is equal to 0 implies that either, and this came up on the last test, right? You guys had to use the fact that if CV is equal to 0, then C is equal to 0, or V is equal to 0. How do I know V is not 0 in this case? That's an eigenvector, right? That requires that you know that this holds for some non-zero V, which forces this to be equal to 0.
How do you change an operator into lambda?
Well, that is the heart of the question, isn't it? Okay,
Okay.
so can I show you how to do it with small examples so I don't have to multiply it all out? Okay, I'm going to give you an expression just like t squared plus t. Suppose that you're looking at t squared plus t. And you apply that to v. So the v, the reason you have to apply it to v is because that lets this happen. If TV is equal to lambda v, what's t squared v? Well, t of TV, which is t of lambda v, which is lambda t of v, which is lambda lambda v, which is lambda squared v. You want to be like do it at length? There you go. Right? So this is equal to lambda squared v plus lambda v. And now we've got numbers instead of operators. And now you can factor the v back out. So this move right here, where you do this polynomial switch, basically what you do is you multiply the v in, use the fact that you can always write down t to the n v is equal to lambda n v for an eigenvector, and then you pull the v back out again once you've done that step. And that's actually why it requires the v has to be in the picture for this to happen. Okay? Yep. Yeah. The easiest way to do it is induction, for sure. We're doing it. The eigenspaces are the core subject of the study in IFC. We'll random the groups there. Yep. The dimension of P of T, you should, okay, be really careful about the word dimension.
Like, I don't know.
Polynomials have degree. The degree of a polynomial is the highest power that occurs, but the degree of a polynomial doesn't tell you anything about the operator.
Okay.
The degree of a polynomial just means what's the highest power that appears. So z squared plus z is degree 2. Operators don't have dimension, right? Vector spaces have dimension, operators don't. So be really careful about separating the use of the word degree, which measures how large a polynomial is, with dimension.
In the proof, for like every alternative with like an eigenvalue, the list went up to T of n and v.
Yep.
And then one of the criteria was like dimension of v is n, which is greater than 0. So I was just kind of confused, like, what was that relationship?
So that has to do with creating a list of, the list of vectors is what tells you that the space has dimension higher than 0. That's because the vectors, v, tv, t squared v, t cubed v, those are vectors that live inside a vector space. So the span of those vectors has a dimension,
Okay,
right? There's a vector space that you're building out with that.
okay, so technically that was kind of like the basis.
Yeah, but it's only because you had vectors. It wasn't t, it was tv, and it was the fact that the number of things in the list told you the dimension. Okay, so let's actually talk a little bit about that exact subject, which is I want to talk about matrix representations of operators. And so we talked a little bit about upper triangular matrices, and so I want to give you the actual theorem here. And then we're going to talk about diagonal matrices, which are even better than upper triangular matrices, and very closely associated with good sets of eigenvectors. So this is not covered on the exam. Okay, this is the back half of 5B, and all of 5C is going to be covered on the final, but not on the exam. Okay. We have a lot to talk about, so we'll spend more time. You guys can come in tomorrow if you got. I'll open up the floor again tomorrow for more specific questions about things that if there's exam prep that you want to talk about, we can have an open floor about that for the beginning of class. Okay, so I'm gonna say again, I'm gonna be a little bit more formal than I rushed through last time. The diagonal of a matrix. You should think of as being A is equal to A11 out to A1M down to AN1 over to ANN. We're assuming here that matrices are square. So n by n matrix is this set of entries starting at the upper left and going to the lower right. So it's the set of entries that of the form AII, where I runs from 1 to n. That's the form to the diagonal. An upper triangular matrix is a matrix that has only zeros under the diagonal. So all 0 under the diagonal. So what I mean by that is the general form that's usually written for this is something like this. Axler gives this particular approach, which is lambda 1 up here down to lambda n in this corner. He writes a big 0 down here and a star up here. The star means could be anything you want above the diagonal. The 0 means everything below the diagonal is 0. So this means everything not including the diagonal. Everything under the diagonal. 0. The star means who cares what's above. The anything. True, false. Diagonal matrix has no zeros on the diagonal. False. What's the stupidest diagonal matrix? Matrix of all zeros is a diagonal matrix. Doesn't look like one. That's a diagonal matrix because there's the diagonal and everything underneath the diagonal is 0, right? Sorry, it's an upper triangular matrix because that's the diagonal, everything underneath the diagonal is 0. It's dumb upper triangular matrix, but it's upper triangle. I mean, it's not dumb in the standpoint that the set of upper triangular matrices is a vector space, but I'll leave that to you. Okay.
Do diagonal and upper triangular on this square?
Yes. You can modify the definitions so that they hold on rectangular matrices, which you'll sometimes see in advanced matrix methods.
Is that helpful at all?
Yeah, I mean, just to point out like where this goes, you know, in the far future, if you guys ever come across something called the singular value decomposition, which works on rectangular matrices, you can talk about things like diagonals that aren't really go all the way through the matrix. So yeah, you have some notion of diagonal that shows up in all kinds of cases. Okay, so here's our first big characterization of when an operator. So the big question is, when does an operator have an upper triangular matrix? Because it would be nice if operators had upper triangular matrices because they're nice. They're nice to work with computationally. They're nice to work with theoretically. They're just nice. They're nice to work with. In fact, almost all of matrix analysis is concerned with special forms of matrices that you can use to make them computationally efficient. So here's the theorem. Let's suppose that T is an operator on some finite dimensional vector space V. We'll pick a basis V1 to Vn. Then the following are equivalent. I'm going to use a notation I haven't used in here before, but I'm going to specify what I mean. So, A, the matrix of T with respect to the basis V1 to Vn is upper triangular. So this notation right here means this is the operator that you're taking the matrix of, and this is the specific basis that you've chosen for your vector space. Remember, matrices, we did all those exercises where the matrix changed with the basis. This is gonna be a theorem about the basis. Which basis of V, which of the bases of V give you upper triangular matrices corresponding to the operator? Okay.
Sorry, what is the acronym?
The following are any one of the condition holding means all of them do. I'm only using these acronyms because I'm trying to introduce you guys to this kind of language because it shows up in all books and upper division classes. Okay. Okay, so the first theorem is about what kind of bases give us an upper triangular matrix, because the second condition says, condition B, which is equivalent to A, says T of Vj is in the span of V1 to Vj for all j. And condition C, span of V1 Vj is invariant under T. The idea of this theorem is, this gives us a way of looking at the basis for a vector space. So the point here is that this theorem characterizes things about a basis that tell you that the matrix is going to be upper triangular. Okay, so if we look at condition B, for example, we try to interpret what this means. What we're saying is, suppose you had a vector space V that was the span of V1, V2, and V3. These are different colors. Then, if TV1 is in the span of V1 and TV2 is in the span of V1 and V2 and TV3 is in the span of V1, V2, and V3, then the matrix that represents T will be upper triangular. In fact, it's almost immediate that it will be upper triangular, because that means that TV1 is equal to C1 V1 plus 0 V2 plus 0 V3. And if TV2 is in the span of V1 V2, that means this is equal to, I guess I'll use it, D1 V1 plus D2 V2 plus 0 V3. I don't need any V3s because it's in the span of V1 and V2. And this would say E1 V1, E2 V2, E3 V3. This is how you compute the columns of the matrix of T. You apply T to the basis and you expand it in the basis. This would tell you that the matrix of T looked like C1 0 0, D1 D2 0, E1 E2 E3. This is why this sort of stacked spanning gives you the matrix that is upper triangular. Okay. So the general proof is basically just this idea. If you have these sort of like stacked up inclusions where TV1 is in the span of V1 and TV2 is only in the span of the vectors V1 and V2, and TV3 is only in the span of V1, V2, and V3, then the matrix has to be upper triangular. Okay. So the other big thing about this is this invariance, because this is what lets us get the eigenvalue thing in. As soon as you see a condition in an argument that has invariant under T inside of it, you should suspect that it's going to be applied to a situation where eigenvalues and eigenvectors show up, because they're the most obvious choices we have for the existence of an invariant subspace. Right? All right. So I actually proved this theorem in the video. I'm not going to prove it again here. You should look at either look at the video or look at the proof in the book. But the point of this theorem is upper triangular matrices, the existence of an upper triangular matrix is a feature of the way that the basis interact with the operator. Right? Either this thing about the stacked spans or this thing about invariance of the span under T. Okay? Are there questions about this that I can answer before I go on? Okay. Make sure you read this argument. It's not a hard argument, or watch my video on it if you haven't done that yet. If you watched it through on 3x speed and you didn't pick up any of the argument, make sure you go back and actually figure out what I said. I know like listening to me talk like a chipmunk is awesome, but
Doesn't C is the span of V1 to VJ being invariant means that T of VJ is in the span.
it's literally the same statement. This is the same exact, that's why B and C are equivalent to each other. To say that this span is invariant under T means that anything in the span maps into the span, right? So is V3 in the span of V1 through V3?
Why do you need B then?
So B gets used because sometimes it's actually easier to check this. It's just I mean, why do you need it? It's a bonus way of writing this. I mean, that's what an equivalence is, right? An equivalence is a way of pointing out different things that you can pivot between without having to argue again, right? So this language is going to make it so that you can use eigenvalues and eigenvectors without having to do anything else, because you've got invariance. And this, or basically, right, it lets you think about invariance of the operator without having to think about what's going on in the background of the spans. Here, it's an explicit argument that the TVJ maps into the span of a certain part of the basis and no more, right? And yeah, I mean, it's pretty obvious that they're equivalent to each other, but it's nice to have both of them. They're different enough that it's worth pointing out. All right, so I still haven't answered the question, which matrices have upper triangular, which operators have upper triangular matrices? And it turns out the answer is all of them do, as long as the vector space you're in is complex. This is one of the most useful theorems in linear algebra, in this sort of linear algebra, which is the theorem. Suppose V is a finite dimensional complex vector space. And let C be an operator on V. And there is basis of V so that the matrix of T is upper triangular. Now, I did this proof in detail in that video. This is an induction proof. It's kind of a weird induction proof because it's not like an induction proof from 248. It's an Axler induction proof, right? Where he just says, well, it's induction. The difference between the way you learn induction the first time, where if you write down a statement that doesn't start with let PS be the statement that something holds for all S less than or equal to K, and then by the induction hypothesis, and it's all this structure like a 5-paragraph essay. That's the way you learn it. And that way your 248 instructor hammers you if you don't write the exact form you're supposed to write. And then the way every working mathematician does it is they say, oh, it's an induction argument. It's obviously true for n equals 1. So just like, just assume it holds for everything up to everything below n, and then just like, kind of wave your hand back. Okay. So in the video, I tried to actually explain why what's going on is going on in the induction. Okay? But it really is just this regular old mathematical induction. Like I said before, Axler trusts you guys, right? He's willing to give you the benefit of the doubt. The idea is that you can use the previous theorem. So where does the induction come from? I'm not going to do the whole proof, but at least I want to point out where the induction comes from in this argument. So the idea is you basically say, suppose that you're working with a vector space V of dimension n. And suppose that if the dimension of U is strictly less than n, then every operator on U has an upper triangular matrix as a basis, so that M of T is upper triangular. Now that looks weird, but this is a setup for an induction. We're saying, suppose that we're working in case n, and suppose that for every smaller case, I can invoke the theorem. And the game is to figure out how to get from an operator on V to an operator on a strictly smaller subspace. Right? So how do you do it? Because if I don't know what I'm trying to prove, right? So what I want to prove, I'm trying to prove. This is the way induction works, right? Induction works by saying, assume something holds for everything less than n, and then show that that forces it to hold for also n, right? That's the basic idea of an induction argument. Suppose it holds for all smaller numbers and show it holds for n. So what we're going to do is we're going to assume that for all dimensions less than n, I can find a basis so that I get an upper triangular matrix. Let's show that that forces it to also be true for n. So what we're trying to prove is that if T is in our V, then there exists a basis V so that the matrix of T is upper triangular. So I need to somehow to invoke the induction hypothesis. I can't be working with V because V is the wrong size. I have to work on a smaller space. So where am I going to get one? Got to get one somewhere. Yep. Sure. What do I know about every operator on a complex vector? Yep. So I don't know that the theorem holds for things of dimension n. I know it holds for anything of dimension less than n, but not for dimension n. Because it's the induction hypothesis. This is an induction argument. I assume that it holds for everything less than n. You just imagine the n equals 1 case is actually really funny because n equals 1, every matrix is upper triangular because it's a matrix with 1 entry. Right? Every operator on a one-dimensional vector space is a scalar. It's like that's the matrix, it's a scalar, right? Which is trivially upper triangular. No way. So yeah. So it's hard to teach up here sometimes. Right. So the idea is this is the induction hypothesis. This is the thing that so we show that it holds for n equals 1. We assume that it holds for anything less than n. And if that was true, and I could use it to show that then it also held for n, then that would mean that I'd have an induction that would give me all sizes, right? I mean, you guys, many of you may still be at the point of your mathematical careers where you look at an induction proof and say, how on earth does this prove anything? It just seems like this vacuous hand-waving thing, and all of a sudden somebody says, well, you just cast this magic spell and it holds for n, all possible n. That's the way I felt about induction forever, right? But at some point, I already rolled out the quote to you guys about how you don't really understand things, you just get used to it. Like this induction is one of those things that eventually you just do, right? But the idea here is if I knew it held for every previous size and I can also prove it holds for the next size, then this was arbitrary, which means if you gave me dimension 2, I'd be able to invoke the dimension 1 theorem. If you gave me dimension 3, I'd be able to invoke the dimension 2 theorem. If you gave me dimension 4, I'd be able to invoke the dimension 3 theorem, right? So the idea is if you could show it for arbitrary dimension, any n you plug in, it's going to work. I know you've all heard the domino analogy, a bunch of the stair-stepping analogy, and none of you believe it. So I'll just leave it like that. You can like exist in your sort of epistemic like your Schrodinger's like epistemology. Right? Just for now, just trust me that induction is that like really smart people like logicians have proved beyond a reasonable doubt that induction is a thing that makes sense in many forms. So if we accept that induction is an appropriate method of proof for a question, we are still faced with the question of how I get from this dimension n vector space that I'm trying to prove, I can find a basis that I can make this operator upper triangular by somehow dropping it down to a space of smaller dimension so I can invoke the induction hypothesis. Somebody's idea was, well, it's complex. Why did I have to assume this was a complex vector space? Somebody already gave the answer out. Because everything has an eigenvalue, right? Every operator has at least one eigenvalue in a complex vector space. So the idea is, okay, well, T is an L of V. T must have an eigenvalue. And we proved that. It's one of the major theorems about operators on complex vector spaces, that every one of them has an eigenvalue. Right? So then what? So then you do this thing where the space that you build that's a smaller is you define the space U to be equal to the range of T minus lambda I. Okay. What do you know about that operator? T minus lambda I. How do I know that U is smaller than V? That's the first question is, how do I even know that U is smaller than V? How can, why is it not surjective? I mean, it has a null space, right? I mean, the whole point is it's an eigenvalue, so it has a null space. And what is the theorem that says that if there's a non-trivial null space, then the thing can't be surjective? It's I mean, you could use the fundamental theorem of linear maps as the easiest way to do it. If the null space has something inside of it, then the range cannot have the right dimension. The dimension of the range must be smaller than the dimension of V. So the dimension of U must be smaller than the dimension of V, because this operator can't be surjective. That means all the rest of the exercise is cleverly applying this to that. This has dimension smaller than n, which means the induction hypothesis applies. And all of the rest of it is basically, then you say, okay, well, if this applies, then that means there was a basis for U that gave rise to an upper triangular matrix. But that means that it had the right span stacking structure. And then you just extend it to a basis for the whole space and argue that that actually is the basis that works for all of these. Okay. This is kind of a weird argument from the standpoint that like it's induction, it's got the big move. The reason I'm highlighting this part of it specifically is this is the hardest part of the argument to understand. What's going on here? And the idea is, in order to imply the induction hypothesis, this must hold. Those look like the same letters. But the reason that holds is because this is an eigenvalue. Notice I'm not working with t here. I'm working with t minus lambda I, so I guarantee that this range is too small. Okay, and all the rest of it is basis chasing. So your assignment, we are going to move on to talk about diagonal matrices, probably either, if I have time to start talking about it tomorrow, I will. Like I said, I'm going to open the floor for review questions if people have them. My intention is to start talking about diagonal matrices. Now, diagonal matrices, I'm actually curious if you guys remember 206. Certainly it is the case, by this argument, that every operator has an upper triangular matrix. There's a basis I can find so that like every operator has an upper triangular matrix. Is that true for diagonal matrices? So a diagonal matrix is a matrix that's even better than an upper triangular matrix. It looks like this. Zeros above and below the diagonal. The nicest possible matrices that exist. Does every operator, and you find a basis for every operator so that you have a diagonal? Why? The Shapiro told you it wasn't true. It has to be invertible. No, that's not actually good enough because, in fact, this is one of my favorite counterexamples in all of linear algebra. This is a cool one. Okay, so this operator. What's the determinant? Well, we're not allowed to say, oh my God, I said determinant. I'm sorry. Oh, I'm sorry. I'm going to just tell you that's an invertible matrix. Oh, I committed sacrilege. By the way, the determinant of that matrix is 1, and so therefore it's invertible. So this is an invertible matrix, but it turns out that if you find it has an eigenvalue of 1, and if you actually compute the eigenvectors of this matrix, there's only one linearly independent eigenvector. So we're going to define eigenspace. The eigenspace associated with 1 is only one dimensional. So in your past, I think I mentioned this last time, you probably have language running around your heads like algebraic degree and geometric degree, and maybe even the fact that this piece of garbage is called defective because it's just not good enough, right? So a defective matrix is a matrix that doesn't have a way, there's no basis that you can use to turn this into a diagonal matrix. And in fact, there's operators that are called defective operators that are going to turn out not to be diagonalizable. And the question of when something has a diagonal matrix is a really deep question. So we're gonna just put our feet in the water around when that can happen with certain kinds of eigenvalues and eigenvectors. And then we're going to move on to inner product spaces after that. So we're going to start talking about diagonal matrices. We're going to move on to inner product spaces. And those of you actually waiting for you in the future, if you take 406 is, what do you do with these to put them in nice forms? And then there's this, you can read ahead in the book if you want. There's a whole chapter on what's called Jordan decompositions and generalized eigenvalues and eigenvectors, which are even better. All right. I'll see you guys.
Why is that not the one on the left?
Why does this not have a basis?
Is it the one on the right or the one on the left?
This one doesn't have a basis.
Okay.
Diagonal, no, so what I'm saying is that there's no basis of this vector space you can choose that makes that diagonal.
Oh,
Wait, why not? Did you go through this?
It turns out to be the case that the theorem is, I'm trying to remind people of the 206 theorem, and the 206 theorem says that if you have if you have eigenvalues that are either distinct or you have two linearly independent eigenvectors, that you can make a matrix where the columns of the matrix are the eigenvectors associated with the eigenvalues. And then so the idea is, if you change basis, you have a diagonal matrix in the middle and you change basis out, but it requires this matrix has to be invertible for this to happen. So eigenvectors turn out to provide things like structural information about what an operator does, if there's enough of them.
For that question, I mean, I'm doing like zero, right? It's not injected. One of them is injected.
No, I mean,
Zero, it's not injected.
Yeah.
So one of them is not injected.
composition of, I actually, yeah, so so is that the one that shows the like compositions with an after zero? Yeah, so that's the other way to, the first way I showed people how to do this, this is my third attempt to explain this in a way people understand. The first way was this way, where you chain these things up and realize, well, if you have a chain of things that aren't injective, something in the chain has to be non-injective.
That's all we got. I don't have anything.
Your stuff, so I have your 4 and 5, I have your 4 and 5. Your revisions are, there's 3 revisions I didn't get to today. That's Brandon did so. And it's like 2 of them are yours. So I'll have them tomorrow. Like I'll have all that stuff going in now. So you're just, it's because you emailed stuff to me and I was like, I want to send stuff over email, but I had to finish it.
Can I ask you a question?